Hello APChem, this is Mr. Koker. We've been working in Chapter 7. This is the second half of Chapter 7 out of the Zumdahl book. In 7.6 we talked about quantum numbers. There are 4 types of quantum numbers that are used to help solve the Schrödinger equation for the quantum model of the atom. The first quantum number N is for energy level. The second quantum number L is for the sublevels S, P, D, and F. The third quantum number M subscript L is for the different orientations for the orbitals in the sublevels. For example, Px, Py, and Pz. Then the third quantum number, or fourth quantum number rather, M sub S, deals with the spin of the electrons in the orbitals, and they can have plus or minus 1/2 spin. So by solving the Schrödinger equation, we can get these probability distributions of electron density plotted. So that's why we call it the cloud model, because these plots look sort of like clouds. And where the clouds have high density, in other words, the dots are close together, that's areas of high probability. And where the dots are far apart are areas of low probability. When you plot these, you do find that certain orbitals have areas where the density goes to 0. Those are called nodes. So one way of looking at that is no density, node. So that's an area of no density. The s orbital is it has a 1s orbital and it does not have a node. But if you're looking in the upper left of the pictures, the 2s orbital does have a node. And so in the graph of electron density as a function of distance, you see the 1s orbital in red. It just goes up to a high probability and comes back down. You see the 2s orbital in yellow, and it goes up a little bit and comes back down to a node, and then goes up again and then comes back down. So it has 2 regions of probability, one near the nucleus and one farther away, and most of the density is farther away than near the nucleus. The 3s orbital has 2 nodes. An area of density near the nucleus, another area a little farther out, and then most of the density is at an area that's farther from the nucleus than the 2s, and the 2s is farther than the 1s. So the idea of the shells is actually a little misleading, because you do have these areas of density that are inside or close to the nucleus in comparison to the other energy levels. But the bulk of the density for the 1s lies inside the 2s, which lies inside the 3s. But you definitely see that they overlap a little bit. The graph, the third graph, shows the density of the 1s, the 2s, and the 2p. Notice the 2p does not have the density that is close to the nucleus, but the 2p appears to have its peak closer to the nucleus than the 2s. However, the little bit of the 2s that is close to the nucleus does cause, in atoms that have more than one electron, it does cause the 2s to have lower energy than the 2p. Your px, py, and pz orbitals are shown over on the right of the top row. The px, the py, and the pz in a particular energy level, such as 2 or 3 or 4, within an energy level, those p orbitals all have exactly the same energy. So when you have that, you say that they are degenerate orbitals. Degenerate orbitals are orbitals with the same energy. And we'll see that Hund's rule applies to those degenerate orbitals. Now when you get to the third energy level, you start having d orbitals. You can see the pictures here. The dxy, the dxz, and the dyz lie along the axes. Actually, I'm sorry, they lie between the axes at a 45-degree angle. The dx squared minus y squared, those have 4 lobes that lie along the x and y axes. The dz squared lies along the z-axis with 2 lobes and a donut around the middle that's in the xy plane. We see in the bottom right the 3d orbital compared to the 4s orbital. The 3d orbital has most of its density closer than the peak of the 4s orbital. However, there is, because the 4s orbital has 3 nodes and 4 peaks, there is the first peak of the 4s that's closer to the nucleus than the 3d, and that's called the penetration effect. In other words, part of the 4s gets very, very close to the nucleus, and that is actually enough to lower the 4s electron's energy lower than the 3d, so the 4s fills up before the 3d. So we get that overlapping between energy levels that's caused by the way in which these orbitals, such as the s, can penetrate close to the nucleus. So we have that picture in the bottom in the middle that sort of shows how the s and the p's and the d's and the f's all add together as a collective to make a sphere of electron density, or a shell, a spherical shell. And then over on the bottom left we see 7 f orbitals. So we see what the f orbitals look like. The fourth quantum number, m sub s, is used for spin, and it can have only one of 2 values, plus or minus 1/2. So one of the principles that we use to talk about the electron filling up of the energy levels is called the Pauli exclusion principle. In a given atom, no 2 electrons can have the same set of 4 quantum numbers, n, l, m sub l, and m sub s. Now they can share n, l, and ml, but they have to have opposite spin, m sub s, and that means that each orbital, and an orbital can be designated using the first 3 quantum numbers. Each orbital can hold 2 electrons, but one has to have a plus 1/2 and the other has to have a minus 1/2 spin. Here we see the orbital notation for an electron that is 1s2, 2s2, 2p6, 3s2, 3p2. Notice the 3p orbitals, px, py, and pz, are degenerate, and it's best to fill one of each instead of double filling, and that's called Hund's rule. Now, if we had atoms that were like the hydrogen atom and had only 1 electron and a nucleus, hydrogen has 1 electron and 1 proton, all the sublevels of a given energy level would have identical energies. For example, 2s and 2p would be equal in energy, or 3s, 3p, and 3d would all have equal energy. But when you have polyelectronic atoms, or atoms that have more than 1 electron, you add in the interactions between the electrons, in other words, the repulsion between electrons within the electron clouds, and that has the effect of splitting the energies within the energy levels into different energies for the different sublevels. For example, the 2s has lower energy than the 2p when you have more than 1 electron. The 3s has less energy than 3p, and 3p has less energy than 3d. In fact, 3d has less energy than 4s. We get that overlapping effect. So our general pattern is that the s orbital has less energy than the p, because the s orbital has more penetration effect. The p orbital has less energy than the d because of, once again, penetration effect. So in particular, the sublevels with more penetration effect have lower energy, and that is because that region that penetrates close to the nucleus is not very well shielded, and so it is more attracted to the nucleus, that portion of the cloud, and that lowers its energy and makes it more strongly bonded to the nucleus to have that penetration effect. So we end up with these energy levels that go from 1s to 2s to 2p to 3s to 3p to 4s to 3d to 4p to 5s to 4d, and so on. The bottom right, you see the how 3s, 3p, and 3d vary in how their electron densities are able to approach the nucleus. And you can see the penetration effect on the 3s, but you also see some penetration effect on the 3p. Remember, the 2p did not have two peaks. The 2p only has one peak. The 3p has two peaks. If you look in the top third one from the left, you can see the 2p in red does not have two humps. So there is no node for the 2p, but the 3p has a node and two regions of high density. The first region doesn't have as much electron cloud density, but the second region is where most of the density lies, but the first region is closer to the nucleus. The 3s has even more penetration effect than the 3p, and the 3s has two nodes. And then the 3d has no node. So there's a bit of a pattern here. If you study it a little bit, I think you'll pick up on the pattern. But the most important thing is to realize that it's this variation in the way the clouds approach the nucleus that causes the splitting of the energy levels into the different sublevels. The different sublevels are actually reflected in the periodic table. However, before the sublevel theories, before the quantum model theory was developed, element patterns were detected by early chemists. In fact, as far back as 1817, Dobereiner was finding patterns in the elements. In fact, the top left shows some of the triads that that's what Dobereiner was calling them, these groups of three elements that he believed were somehow related in their properties. And you find that the triads that he detected back then are in fact members of the same families in today's periodic table. Newlands in 1864 developed his law of octaves. In fact, the British would argue that he deserves to get credit for the first periodic table because his preceded Myers and Mendeleev's by 5 years. His law of octaves is that every eighth element has similar properties. Just like every eighth note on the piano has the same note, just a different octave. Lothar Meyer in Germany and Dmitry Mendeleev in Russia were working at the same time and developing periodic tables. Mendeleev generally gets the greatest amount of credit for his periodic table. One thing that he did with his table was that he found that there were gaps in his table, and he basically predicted the existence of those elements and wrote down what their properties would be. And then a few decades later, when those were discovered, they were found to fit perfectly with the predictions that he gave them. And so that helped to prove his periodic law, or his idea of a periodic table, was in fact correct. So today we have a periodic table that has a lot of incredible value as a tool for chemists, but we find that it also is more than just a place to look up numbers and names and symbols, but it also shows the pattern of the elements. Of course, the pattern of the elements comes back to the pattern of the electron energy levels, and the S, P, D, and F blocks of the table come back to the S, P, D, and F sublevels and as parts of the energy levels in the quantum model. So we would say that quantum theory explains the periodic law. The law describes the behavior of elements. The periodic law is explained by the quantum theory. So here we see that the periodic table has 4 blocks, just like we have 4 sublevels that fill up with electrons in the quantum model. You have the block in blue that is the s orbitals, The red block in the middle are the d orbitals, the greens are the p orbitals, and the yellows are the f orbitals. Now, to fill up the atoms with electrons, we take advantage of the Aufbau principle, which says that the lowest energy levels fill up first, and that includes sublevels. So 1s gets 1 electron for hydrogen, 2 electrons for helium. For lithium, you fill up the 1s, then you put 1 electron in the 2s. For sodium, you fill up the 1s, the 2s, and the 2p's, and put 1 electron in the 3s. Notice hydrogen, lithium, and sodium all have 1 electron in an s orbital. Hydrogen, lithium, and sodium are in the same family on the periodic table. So the valence electron energy levels are the key to understanding the Aufbau principle and the filling up of the electrons in the atoms, and also the pattern of the periodic table. Hund's rule says that if you have degenerate orbitals, for example, we see oxygen has 4 electrons in the 2p, you would have the option of putting 2 in the first 2p and 2 in the second, but that's not what you do. When you have degenerate orbitals, you put 1 in each before double filling. And so the 4 electrons in oxygen are as spread out as possible in the 2p orbitals. The key to understanding the link between the chemistry of the atoms and the periodic table and the filling up of the electron energy levels and sublevels is to focus on the valence electrons, the electrons in the outermost principal quantum level. The core electrons are the ones that are in the inner levels, and those are generally stable and will not participate at all in bonding or interactions between atoms. And so we focus on how many electrons are in the valence shell. Also, what sublevels are filling up. Now, you will find as you study this in more detail that there are some of the filling of particularly the D's and the F's that are a little bit out of order. We have the diagonal rule in the bottom left that shows the order of the filling. Sometimes you will get one that you expect to go into a D, but it goes into an F or something like that. You don't need to know all those exceptions for the AP test. The AP test will not cover the exceptions to the rules. We have names for the different segments of the periodic table. We call the S and the P elements, the ones in the blue and green on here, we call those the main group elements. Those are the ones that it's simple to predict the charge of the ions using the position in the table. The middle of the table, the D block, are called the transition metals, and then the bottom long 2 rows are called the inner transition metals, and also known the top row as the lanthanide series and the bottom row as the actinide series. Periodic trends in atomic properties can be predicted by analyzing the properties of the electron clouds, how they interact with the nucleus, and how the clouds interact with each other. So if you can reason out the electron clouds and their interactions with the nucleus and with the other portions of the cloud, in other words, the other sublevels, then you can generally get a handle on why atoms have the properties that they do. It's important to remember Coulombs Law here. Coulombs Law says that opposite charges attract, so the nucleus attracts the electrons. It also says that like charges repel, so electrons repel each other. And that can create a bit of a shielding effect. We say that the inner electrons shield the valence electrons from the nucleus. The greater amount of charge you have, +1, +2, +3, -1, -2, -3, the greater amount of charge increases the attraction or repulsion. And as you increase the distance, in other words, as electrons move to higher energy levels and are farther from the nucleus, the attraction decreases. As the distance decreases, the attraction increases. So Coulomb's law has to do with distance r and the amount of charge q. So you see q being in the numerator means that a greater amount of charge has a greater force of attraction. R being in the numerator and being squared means that increase in the distance lowers the force of attraction. The amount of nuclear charge can affect how strongly the electrons are drawn towards the nucleus. So in other words, atoms with a higher atomic number Z attract their electrons with a greater attraction. However, inner electrons or core electrons can shield the valence electrons from the nucleus, and that diminishes the effect of the nuclear charge. And so we say that the Z effective or effective nuclear charge is subtracted by or diminished by the shielding effect. There are sublevel effects that can also affect certain atomic properties, and we'll see that as we look at some of these trends. Let's start with the first periodic trend being ionization energy. That's the energy to remove an electron from a gaseous atom. So in other words, if you start with atom X and you put in the ionization energy, you'll get the ion X plus 1 and the electron will be removed. So effectively what you're doing is you're moving the electron from its valence shell to the infinity energy level, E infinity, where E is equal to 0. Remember, the energies are negative when they're in the energy levels and 0 when the electron is out of the atom. And this is measuring the potential energy. That's what we're measuring here. So we see it for hydrogen that if the electron is in the first energy level and you move it all the way to the N equal infinity energy level, that you have to put in 1312 kilojoules to do that to a mole of electrons. So you have to put in 1312 kilojoules per mole to ionize hydrogen because the energy level N equals 1 is at negative 1312 kilojoules per mole and N infinity is at 0. Now when you compare the 1312 number to helium, helium's almost up there at 25, so that's almost double the amount of ionization energy as hydrogen. And that has to do because helium has double the nuclear charge. So its Q1 is double the Q1 of hydrogen in the Coulombs Law equation. We see that lithium is way down around 500, and that's because lithium has electrons in the second energy level. It has a 2s electron, and the 2s electron is farther from the nucleus. Even though lithium has an extra proton, 3 protons, the energy level in the 2s is farther from the nucleus and also quite effectively shielded by the 1s. In other words, the 1s is pushing the 2s electron outward, and that is canceling out quite a bit of the nuclear charge of the 3 protons of the lithium atom. We see a general trend as you go from lithium to neon of increasing ionization energy. You do get a couple of hiccups between beryllium and boron, and that's because beryllium is in a 2s, and the 2s has that penetration effect. The 2p electron of boron does not get the penetration effect of the 2s, and so that lowers its energy. So even though boron has 1 more proton than beryllium, it is slightly easier to remove the electron from boron than from beryllium. We have boron with its 2p1 and carbon with its 2p2 and nitrogen with its 2p3. But then again, we see another hiccup between nitrogen and oxygen, and that is actually due to the fact that oxygen double fills one of the orbitals in the 2p. So the extra repulsion created by double filling that 2p orbital cancels out the extra proton of the oxygen, and the effect is that it actually lowers instead of raises. So the general trend is more protons, the electrons are held more tightly, and it's harder to remove the electrons, so the ionization energy goes up. But we do see some sublevel effects where we get the hiccup between beryllium and boron, and then the double filling of oxygen compared to nitrogen. Notice after neon, the energy to remove the electron goes back down because now we have the sodium atom with a 3s electron. The 3s electron is very well shielded by the 1s, the 2s, and the 2p electrons of the first 10 electrons in the first two sublevels, or first two energy levels. And so the shielding effect causes sodium to be easier to remove an electron from. I think if you compare elements in the same family, such as lithium, sodium, and potassium, those would be the bottoms of these three curves, and those do show a slight decrease in ionization energy as you go down the chart from lithium to sodium to potassium. We also see it more pronounced with helium, neon, argon, krypton, xenon, radon. We see that the electrons are getting easier to remove as they are farther from the nucleus, and usually very well shielded by the nuclear or by the core electrons. We see between sodium and argon, we get those same two hiccups when you change from s to p orbitals and when you change from being half filled in the p orbitals to double filled. Notice for the d orbitals and the f orbitals, you do get fairly level, slightly increasing but fairly level. Now those are actually inner energy levels, and so you are adding a proton to the nucleus while adding an electron to an inside level, and so you almost get 100% shielding, canceling out the effect of adding the nuclear proton. So that's why they're practically level in the d orbitals and the f orbitals here. So I encourage you to sort of study sort of the ups and downs of this graph, and as you look at the ups and downs, think about what energy levels and sublevels are being filled, and see if you can reason out some of the little idiosyncrasies of this graph as far as trends within families, and then little trends within rows, and then the places where it sort of separates from the trend and does something a little different, like the little hiccups. It's also instructive to look at successive ionization energies. In other words, not just the energy to remove the first electron, but once you've removed the first electron, what is the energy to remove the second? Now, as you can see from this chart, the ionization energies go up as you remove more and more electrons, because as you remove electrons, there's less repulsion in the cloud, and so the nucleus can do a more effective job of holding on to the electrons as you remove 1 and then 2 and then 3 and then 4 electrons. So it gets harder to remove electrons as you remove more and more of the electrons. The second ionization energy of helium is almost, in fact, it's more than double the ionization energy of the first electron to come out of helium. The second ionization of lithium is over 10 times the first ionization energy of lithium. Now you might think, why is it just barely double for helium, but more than 10 times between first and second ionization energy for lithium? Well, for lithium, the first electron you remove comes from the 2s, but the second and third electrons have to come from the 1s. And so the electrons in the 1s are closer to the nucleus and not as well shielded as the electron in the 2s. So if you're looking at these successive ionization energies, you can tell when you get a big jump that you are changing energy levels. So we see the big jump between for lithium between the first and the second, and that tells me lithium has 1 valence electron. We see for beryllium the big jump is between the second and the third, which tells me beryllium has 2 electrons. We see for boron the big jump is between the third and the fourth, and that is because boron has 3 valence electrons. One thing to notice is there's not as big a jump between the second and third ionization energy of boron as compared to the first and second. Notice the first and second, it's practically a 3 times 801 and 2427. That's over 3 times the ionization energy. But then there's only an increase of a little over 1200 for the second and third ionization energy. And that's because the first ionization energy of boron comes from the 2p or electron, which has higher energy than the 2s, which is the second ionization energy of boron. Then, of course, we see the big jump between the third and the fourth. So you might want to just kind of look at some of these and see some of the patterns. Generally, as you go left to right, the higher the ionization energy, the more electrons you're trying to remove, the harder it gets. But you can see some little effects due to differences in sublevels and differences in energy levels. One of the ways that we study these energy levels and sublevels is we can verify them using something called photoelectron spectroscopy. Encourage you to read this section in the book. AP has put photoelectron spectroscopy on the AP test. Since about 2014, they've been doing photoelectron spectroscopy questions. Generally, to understand the process, you use high energy X-rays, which are high enough energy to promote any electron in the atom out of the atom and into ionization state. And so we're not just removing the valence electrons as we see with the ionization energy graphs and tables, but we're removing any electron in the atom. So for an atom that has 5 electrons, we might remove the 1s, we might remove the 2s, we might be removing the 2p. What you do is you use X-ray photons that have constant energy, and then you look at how much kinetic energy left over after jumping out of the atom, how much kinetic energy is left over in the electrons that are removed. And so by looking at the amount of leftover energy they have, you can tell how much energy had to be expended from the X-ray to remove the electron from the atom. So the analogy I like to use is if every day your mom gives you $10 for lunch, and then every night when she does laundry, she cleans out your pockets, she can know how much money you spent on lunch by how much money is left in your pocket. So if on one day she gives you $10 and when you come home you have $3 left in your pocket, she knows you spent $7 on lunch. If another day you come home and there's $5 left in your pocket, she knows you only spent $5 of the 10 that she gave you. So in the same way, we use photons of equal energy every time, but then by looking at how much energy from that photon was to remove the electron from the atom, and then how much energy was left over for kinetic energy for the electrons, we're able to calculate the amount of energy it took to remove the electron from the atom each time that we removed it. So for helium, we find that helium has 2 electrons and that they both have the same amount of energy to remove, and so we only get 1 peak, but the size of the peak is showing us that there are 2 electrons in that peak. For neon, we find that there are 3 different amounts of kinetic energy for the removed electrons, meaning that the electrons have 3 different levels of potential energy when they're in the atom. So we have the 1s, the 2s, and the 2p. The size of the 2p peak shows that it has 3 times more electrons in it than the 2s or the 1s. So the size of the peaks can tell us how many electrons are in each sublevel, and the energy of the peaks show us from low to high how many sublevels the atom has. So for argon, we find we have 5 peaks that correspond to the 1s, the 2s, the 2p, the 3s, and the 3p. So we will be doing a photoelectron spectroscopy activity on a worksheet this week to practice our interpretation of PES diagrams like these, or graphs like these. Electron affinity is another quantity or property of the atom that can be used to study the energy levels of the atom. And one thing to note for electron affinity is defined to be the energy change associated with adding electrons to a gaseous atom. So if we think of an atom bonding to a new electron or adding electron to an atom to make a negative ion, an anion, if the atom receives the electron by attracting it to itself, then that means we are forming a bond, and forming a bond gives off energy, and that is exothermic, and so the energy should be a negative number because energy is released when a bond forms. So if you followed all that reasoning, any of the atoms on this graph to the right show that they have an attraction or an affinity for electrons. Any atoms that are above the zero and in the positive part are atoms that reject receiving an extra electron to make a negative ion. So we can learn a lot, not just about filling up energy levels, but also sublevels. So we see that hydrogen and lithium both have negative electron affinities, kind of like hydrogen, lithium, sodium, and potassium, but that's because they are all S1 and can put one more electron in the s orbital. Helium does not want another electron, nor does beryllium, because you would then have to start for helium, the next energy level, to add an electron. You'd have to go from 1s2 to 2s1. You'd have to add a new energy level, and that's not favorable. For beryllium, you'd actually have to add a new sublevel. So beryllium, you're going from 2s to 2p, so beryllium does not want an extra electron. Boron and carbon, you already have the 2p electron started, and so you're adding to a sublevel you've already begun. Nitrogen is right up there around 0 because, and it's higher on the graph because it doesn't want an electron because an extra electron double fills. So we can see here that fluorine and chlorine have the highest amount of electron affinity. Now you might expect fluorine with the smaller atom to have a higher electron affinity than chlorine, but in fact it's slightly less negative because of the small size of the fluorine 2p sublevel. It actually creates more repulsion to add an extra electron, and they're a little more packed in a little bit too tightly for fluorine. Chlorine has larger 3p orbitals and a little more space, and so chlorine is slightly more favorable to add an electron than for fluorine. And so you might look at some of these others between neon and sodium, magnesium, aluminum, silicon, phosphorus, and look at kind of some of the ups and downs. Remember, if it's going up, it's because it wants electrons less, and if it's way down on the chart, that's because it wants electrons more. This is the energy for adding an electron to the atom. Another periodic trend is the idea of atomic radius. Atomic radius can be difficult to define because the cloud really doesn't have an edge to it. But one way to look at atomic radius is the covalent radius. So if we think of an F2 molecule, if we take the distance between the nuclei of the F and the other F in F2, half that distance could be called the radius of a fluorine atom. So this graph on the left shows that as nuclear charge increases, that atomic radius decreases from left to right, and so that's just getting a stronger nucleus, pulls the electron cloud in tighter. We also see as you go down the chart that atomic radius increases, and that is because you're adding more energy levels, and that causes an increase. There's generally pretty constant in the D's and the F's, and that is because each new proton added is practically completely canceled out by an inner core electron being added to a D or an F orbital. Remember, D's and F's are inside the valence shell. They are not part of the valence shell. Only the S and P's are ever in the valence electrons portion of the atom. So these are core electrons that you're adding. And a core electron is a shielding electron. So you add a proton plus 1, but you also add a core electron minus 1, and they basically cancel out. The shielding effect cancels out the extra nuclear charge. We also see that adding electrons to make negative ions over here in the red, in the bottom right, that makes the atoms quite a bit larger than the ions are quite a bit larger than their atoms. The more electrons you add, the bigger the ion. One exercise would be to look at, before I move on, the positive ions are quite a bit smaller. Typically for the cations, you remove an entire energy level of electrons to make the cations. One thing to look at here is to look at atoms and ions that have the same amount of electrons, or isoelectronic. So N3 minus has 10 electrons, O2 minus has 10, F minus has 10, and neon has 10. But they'd have different numbers of protons. Nitride would only have 7 protons, and neon would have 10. So there's a progression in size if you have the same number of electrons filling up the same orbitals, but you have different numbers of protons to hold on to those electrons with. The sodium ion would be even smaller than the neon atom, and the magnesium ion would be even smaller than the sodium ion. And that's because magnesium would be holding on to, magnesium plus 2 holds on to 10 electrons with 12 protons, compared to 11 for sodium, 10 for neon, 9 for fluoride, 8 for oxide, and 7 for nitride. So you can get a lot of information out of these position on the periodic table, but also the nuclear charge, the sublevels and energy levels that are filling up, the number of energy levels, the shielding effect, and AP loves to ask questions about the trends in the periodic table properties of ionization energy, atomic radius, ion radius, and electron affinity. I will tell you that one thing you never want to use to explain a trend is to say something like the atoms want to have a full outer level. That's a big no-no in AP Chem to say that the atoms want to have a full outer level. If I take the example of neon, neon is a very stable atom, and it does have a full outer level. However, the explanation for why neon is stable does not have to do with it having a full outer level. In fact, full creates more repulsion, which should create more shielding effect, which should make electrons easier to remove. However, neon has the strongest nucleus in its row. It's because neon has the strongest nucleus in its row that it is hardest to remove electrons from neon, and neon has the smallest atomic radius. So focus on things like nuclear charge and repulsion between electrons when trying to explain these trends. Stay away from explanations such as noble gas arrangements are stable or full shells are stable. That's just not true, and it doesn't explain the effects. Finally, we want to sum up here by looking at how you can use the periodic table to predict properties. The vertical columns of the periodic table are groups, and those vertical columns have similar electron configurations. For example, in the first column, lithium, sodium, potassium, rubidium, cesium all have S1 arrangements, just in different energy levels. It's the number and type of valence electrons that primarily determines an atom's chemistry. Properties such as melting point can be seen here. Lithium has the highest melting point. lithium and sodium, potassium, rubidium, and cesium all have one valence electron to bond the atoms together with metallic bonds. However, the lithium atoms are smaller, which means the one valence electron is more concentrated than in the larger atoms such as sodium, potassium, rubidium, and cesium. So the melting point trend actually has to do with atomic radius and how that causes the one valence electron per atom to be thinned out. So I like to think of the difference between taking a tablespoon of peanut butter and using it to stick ping pong balls together versus using the same 1 tablespoon or 1 electron per atom of peanut butter and trying to stick, say, basketballs together. You'd have to spread the peanut butter very thin on a basketball, but it can be spread on thickly on a ping pong ball. The density of the elements are increasing as you go down the chart for lithium through cesium, and that has to do with the larger, the mass growing at a higher rate than the radius or the volume rather of the atoms. So the mass grows faster than the volume does. The atomic radius from lithium to cesium is is less than 2, a factor of 2, which when you cube it would be a factor of 8. But cesium is a lot more than 8 times the mass of lithium. Lithium's mass is around 7, and 8 times 7 is 56, and cesium is heavier than 56. So the mass grows at a faster rate than the radius does. The ionization energy, the first ionization energy of lithium through cesium shrinks from 520 to 496 to 419 to 403 to 376, and that's due to the changing of energy levels from level 2 to level 6 creates a greater distance and quite a bit of shielding. So the cesium atom is easier to move the electron from than the lithium atom. So you can determine the properties from the location on the periodic table. We have different names for the different groups, such as alkali metals, alkaline earth metals, transition metals, halogens, noble gases, metals, nonmetals, metalloids, lanthanide series, actinide series. And it's very useful to learn the names of those groups, because very often in the book and in my notes you'll find me referring to them by those names. The properties of the alkali metals are one example of how you can figure out the properties by looking at the atomic properties and their trends on the periodic table. Thank you for listening. This is the end of Chapter 7.